we need to cover one more basic numerical representation technique before moving on to how computers actually store numbers and how they cover the entire range of precision that we'll need for accurate calculation. This goes all the way back to high school type operations, but a refresher is always welcome. The textbook continually uses the number 6,519.23 as their example. So, of course, in this case, if you want to represent this in scientific notation, you'd move the decimal spot over 3 places to obtain 6.51923, and we have to multiply that by 10 to the third, which would be 1,000, which makes sense. It's 6,519, so if you multiply that exact number times 1,000, you would get the original answer. Scientific notation, and of course the number of significant figures is important when using this. In this case, we would have 6 significant figures because there are no leading or trailing zeros. So the number of digits stored all the way to the front, all the way to the back, is what really, in the end, is important. The exponent is handy for placing that precision wherever you want it in the magnitude scale. When you hear people talking about, oh, it's an order of magnitude better, an order of magnitude worse, that's what they're talking about. Like 10 to the fourth would be an order of magnitude bigger than 10 to the third. That's what the expression is referring to. For reasons that will become apparent fairly soon, binary representations in the floating point system, which is what we're going towards discussion, will always have a leading 1. So let's just write that out. Be 1 point, some number, b. You have however many significant figures you might want to add to that. And you multiply that by by some exponent, a. So in binary system, they actually just refer to this unknown series of b digits as the mantissa, and this series of a's up here in the exponent of 10 to the whatever power is, well, it's called the exponent. That makes sense. So the reason we can say in binary that we'll always end up with a 1 point something 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 number, that, for example, let's take the number 50. The way they represent this, the number 50 in binary floating point systems, so this is how the number 50 is saved onto your hard drive in a computer. It's how it's communicated across the internet when you order 50 copies of Top Gun off Amazon or something. I don't know. You take the number 50 and you look back in the handy dandy table of powers of 2 for the power of 2 that is smaller, just smaller than the value you're looking at. So 2 to the 6th, the 64 is too big. 2 to the 5th would be 32. That works just right. So we'll take 50 divided by 2 to the 5th, which is 32. So this in the end it becomes 50 divided by 32. And if we pull that math out, that becomes 1.5625. Of course, we have to multiply this back to get us right back to where we came from. But this is now useful. We have the mantissa, and we have the exponent that allows us to represent this number in binary. And so they have a very specific order of bits that represents how this number should be shown. So we'll go back to your textbook real quick. Look at the document camera here. The first bit. So in this case, if you're going to store a double precision floating point value, double precision meaning it's actually storing 64 bits of information. A bit is, again, each individual switch. It can be a 1 or it can be a 0, as indicated by these colored or uncolored boxes here in the series. Of course, a byte is 8 bits. That's just a bit of computer knowledge for you. So you have either single precision, which is a 32-bit number, or a double precision number, which is stored in 64 bits. And really what that ends up meaning is just you are storing more precision for the mantissa and more precision for the exponent. So the mantissa for a 64-bit number is actually 52 bits long. So you can have seemingly 52 different exponents. But note, if you look at the exponents, it's actually not evenly biased, 2 to the negative 1, 2 to the negative 2, 2 to the negative 3, all the way down to 2 to the negative 52, knowing that the mantissa will always be a fraction of 1. It is because we divide the base number by the next smallest power of 2. That means we'll always be storing a 1 point something, a 1 point mantissa times 2 to the exponent form. So in this saving form, we have the sign bit, which of course indicates whether it's a positive or negative number. I believe in this case, a 1 is a positive, 0 corresponds to positive, 1 corresponds to negative. And then you store the exponent plus something called the bias, which is kind of interesting. So if you were going to store a number that was massively positive, a very, very large number, 10,000, 50,000, 500 million, you have an exponent value which is very, very positive. If you had something you were wanting to save that was very, very, very small, say a number to the negative 20 or 1/1000th, something very tiny, you would end up, in that case, if we look back at the main screen, say you're wanting to save the number somewhere near the order of 0.03. So you'd be here times 2 to the negative 5th. So that exponent now has a value of negative 5. But if we look at the framework we have to fit into, how would you represent the value negative 5 in the exponent? Does that mean now that your exponent has to have another binary digit so that it can be switched negative when necessary? That's just taking up space. It seems like redundant information. And space is what this is really all about. The more slots you take up with useless signage, every spot represents a loss of precision, represents a loss of range of numeric values that can be represented. So what they've done instead is introduced the concept of bias. In this case, we only need, I think, a power of 4 for the example that's written. Now, the largest number that can be written with 11 bits is 2047. That's when all 11 bits become a value of 1. So if you look here on the main screen, if you look back to that page, you say 2 to the 11th, that actually comes up to 2048. But the largest you can represent, for other reasons we'll cover in a second, is 2047. So that can be a very, very large exponent. But the bias that is introduced has a value of 1023. So if you need an exponent of 4, you add that to the bias of 1023, you actually end up saving a value of 1027. That allows you to represent both a positive and negative range of exponents with a bit of reduced magnitude, but really how often do you save a value with something to the positive 10 to the 27th in magnitude? So it allows you to represent both positive and negative numbers very, very accurately. So moving forward into an actual example, looking at the same framework, this system right now is saving the number 22.5. So hopefully we can step right through the same type of setup. So if we start with a value of 22.5, we would look in our table to see the value in binary that is smaller but closest. So 2 to the 5th is 32, 2 to the 4th is 16. So obviously 22.5 lays between those two. So we will use 2 to the 4th essentially kind of as a scaling value. That has a value of 16. Of course, so that we're not breaking the laws of mathematics, we have to multiply by 2 to the 4th. This ends up giving us the saving value of 1.40625 times 2 to the 4th. The 1.40625 is just 27.5 divided by 2 to the 4th. 22.5 divided by 16. So the mantissa, again, you drop the 1, you're only going to be saving 0.40625, and the exponent we're interested in is 4. This is, of course, a positive value, so if we start writing out all the digits, we start with the indication of if it's positive or negative. Again, just to confirm and reinforce, 0 for the first digit corresponds to positive, so we will start with a 0 bit. 1 would be representing a negative number. So the next number in sequence, this is our, I'll start labeling these. This is sign. The next bit in the series would be the exponent, plus its bias. Oh, come on. And this will be 11 digits. Even if you don't need 11 digits to represent your exponent, it still holds 11 spots, just so that we follow the numerical standard for saving a double precision number. In this case, we need the exponent of 4. But we have to introduce the bias. So we would say we need to represent in binary the number 4 plus 1023. This is the default double precision floating point bias. You'll use that every time. So this is, of course, 1027. And that can be represented in binary form by 1, get all the zeros right, 0, 0, 0, 3 more zeros, and the first time you write this out, you'll realize why we as humans do not communicate with the binary system. Okay, so that is both the sign bit, all the exponent bits taken care of, and now the mantissa would be written out. And at this point, you're looking to represent just the 40625. Technically, it's 0.40625 as the mantissa value of this digit. And of course, we can go now and look at this table, referencing the answer. It's a bit harder to find otherwise, but if we can just sum this up, equals -2 plus -3 plus a -5, that should very accurately represent 0.40625. So those are the binary bits we'll be writing into this representation. So it would be 01101. That's actually all the information we need to represent the entire mantissa. So everything else out to the 52nd bit of the mantissa would be 0. So we don't need those small chunks. Of course, every step you take over here to the right represents a smaller and smaller and smaller and smaller component of a value. So that is how you lay out a number in binary double floating point precision value. First is a sign bit, then you go to the exponent bits, and then lastly go to the mantissa bits. As is common sense, the more bits you have representing the mantissa, the more accurate representation of the number you can achieve. This is why a 64-bit system is more precise. A double precision value is more precise than a single precision. This shouldn't be confused that a 32-bit system or a smaller system cannot operate in higher precision levels. It's possible for it to. It's just not natively functioning there. So this does lead to the question of limits. We pursue double precision over single because it raises the limits. It raises the bar. It allows us to be more precise. So why bother, and what are the limits? In terms of absolute range, you need to be concerned with underflow and overflow in both a positive and negative sense. These numbers are either exceedingly small or exceedingly large. You've heard a lot about overflow, and it's sometimes referenced in software problems, or some older computers that didn't have protections we have now would have problems with overflow in simple software. But overflow in the positive sense represents roughly 1.8 times 10 to the 308th. So you need to have a pretty big number to overflow a double precision value. The single precision overflow is not nearly as high. Yeah, that makes sense. On the negative side, it also is common sense to see that it would be the same value but negative for overflow in the negative direction. Now don't confuse that with underflow. Just because it's a negative value doesn't mean that we're underflowing the whole range. This is actually overflow of magnitude. So whenever you hear underflow or overflow, it'll probably be a nice exam problem. Think about the magnitude of the value you're storing, because in the end it's just one little bit at the front that represents the sign. The only difference between representing 1.8 times 10 to the 308 or negative 1.8 times 10 to the 308 is just flipping that initial sign bit. Not a big deal. So an overflow means you're not able to represent that large of a number. I don't know what you're measuring that ended up with a number that big, but there you are. The idea of underflow comes from the fact that you're now in this range of very tiny numbers. So the smallest number that you can represent in a double precision value is 2.2 times 10 to the negative 308. Makes sense that the exponent is the same, 308 in both cases, because we have that evenly biased offset. So in this case, 2.2 times 10 to the negative 308 is the smallest value you can store in a double precision number. Again, if you're taking direct measurements, I don't think there's a sensor in existence that can measure any value that small. The reason we even pursue storing numbers of this large and small magnitude at all is for the intermediate calculation steps. It might be that the numerator, it might be that one component of a large formula you're calculating, or the subtraction of two values divided by something else ends up with this very, very tiny intermediate step. And these intermediate steps lead us to the discussion of errors. There are two distinct types of errors that can be discussed in numerics. Roundoff error and truncation error. So the combination of these can be combined to create the total error. Now, round-off is exactly what you would expect. If you have some big number, 2.6137526 blah, 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 just perhaps it's irrational and goes on forever. If you have rounded off that digit, say you just wanted 6 sig figs, you erase that trailing data, guess what? You have error. If this was an intermediate calculation and you erased that trailing precision, it's gone. That you've introduced an error on the order of, what would it be, 10, 100,000, millionth, be on the order of a millionth on that description, on that problem. If you've ever run into issues with the final calculation on an exam due to not carrying enough significant figures in a calculation, that is roundoff error. So, sometimes working a problem, it's handy to solve it in chunks, but perhaps on your page you don't write down all 10, 11, however many digits your calculator presents. You certainly don't type all 10 or 11 digits back into your calculator to carry that precision forward with you. If you are not operating with the same saved value in digital form that you left your calculator storing, you've lost that precision. So roundoff error, pretty simple, but keep in mind that can be a problem. Now, there are two ways to obviously round. In this case, if we wanted to squeeze this down to 5 significant figures instead of 6, you can follow the standard rounding rules, and this would become 2.6138, because if 5 or greater, you round up, because it's closer to the next value, a high. 5 or less than 5, you round down. So this is rounding as you know it. But as you might expect, that takes cycles for a computer to figure out. You have to check a certain bit value, and you have to then round up. I mean, of course, that operation can be performed, but it just takes time. With low-power computers, or in circumstances where you want a high-power computer to solve a problem very, very, very fast, that will stack up if you have to do this a few billion times in your solution. The other thing that can be done is you just truncate. 2.6137. You just knock off the 5 It could be a 9, and you just truncate down. But again, that is now introducing significant error. When it comes down to you having to have an understanding of how much does that error add up, how much does it matter for the problem you're solving, how much does it change your solution in the end. So truncation or chopping versus true rounding of a number, again, still falls off in round-off error. It would still be in the round-off category. Truncation, as an entirely separate category, comes from truncation of sequences and series that represent continuous functions in numeric form. You will find in the rest of this class that many parts of the numeric theory developed will follow series. Taylor series is one of the most common. So in this case, for an example with Taylor series, if you want to represent sine x, the Taylor series expansion of that, which of course we probably all have to just go take a quick look up, would be x minus x to the third over 3 factorial plus x to the fifth divided by 5 factorial. And you just keep going on and on and on. If I ask you the question, how many of these terms do you have to list to arrive at a full definition of sine x in a Taylor series form, the answer has to be infinite. It just keeps going. Now, the answer between how many do you have to be useful versus how many do you have to be perfectly accurate is very different. In this case, we have 1, 2, 3, 4, 5, 6 different terms for the expansion of sine x. This should be a fairly accurate solution. Of course, if you had 7, it would be better. If you had 10 terms, it would be even better than 7. If you had 1,000 terms, it would be better than 10. But what's the limit? What's good enough? And it just comes down to the specifics of your problem. That becomes down to how sensitive a particular continuous function may be to the number of Taylor series terms. A lot of the theory we cover in this first introduction to numerics will just do maybe 1 or 2 or 3 terms. The first term is generally just a linear addition, not a big problem. But Taylor series truncation is a serious form of error in numerics. It's part of the main reasons that we pursue iterative solutions. We use it as a basis for marrying continuous functions to our discrete numeric equivalents. But know that as you see repeatedly in the textbook and repeatedly in the examples, as you see me talk about, we'll just take the first 2 terms of the Taylor series expansion. That immediately introduces truncation error. But then again, we're saving so little by putting in terms 3 through 10,000 that it's easier oftentimes just to have the numeric method iterate and you solve the problem. So those are the 2 components of total error. Roundoff error, truncation error, formed to create total error. And that error is described as the difference in numerical representation from the actual algebraic truth. However it arises, whether it's due to saving a number in the machine, whether it's due to error propagation through intermediate calculations, or whether it's due to pure truncation of series expansions, that error matters, it adds up, and it can affect your final solution.